Hi there, and welcome back to Find Solve Explain. Today we're going to go over BMO2 2017 question 2. This is a fairly fun question, which involves a rather unique sequence that you have to investigate. In particular, proving that an plus 1 is greater than an for infinitely many n, and also determining whether an plus 1 is smaller than an for infinitely many n. The full question says, let the floor of x denote the greatest integer that is less than or equal to the real number x. Consider the sequence a1, a2 defined by an is equal to 1 over n, open brackets, the floor of n over 1 plus the floor of n over 2 plus the floor of n over 3, and so on until you get to the floor of n over n. A few interesting things to note when we first see this sequence are, first of all, that for the first term of each one is obviously going to be 1, because the floor of n over 1 is just n, as there's no decimal part for integers n, and that n divided by n is 1. So automatically you have 1 plus then the floor of n over 2 over n, and so on, all the way up to then what ends up being 1 over n, because n over n is just 1. So the first thing that I noticed, at least, is that every time you have more factors in this sequence, effectively this will only change when a factor changes. For example, if a number is odd, then the n over 2, the floor of n over 2 is the same as the floor of n minus 1 over 2. This immediately gives one idea, which is what happens if we have certain prime numbers in this sequence. Well, in reality, it's fairly easy. The first number, that is the floor of n over 1, increases by 1, because you have, so take n equals p for some prime. You have p over 1 instead of p minus 1 over 1. And then you also have an additional final term as the floor of p over p did not exist before. For all others, because no divisors change, the floor of p over 2, for example, is equal to the floor of p minus 1 over 2. And this also applies for 3 and 4 and so on, because prime's only factors are themselves in 1. So, now that we've covered that, we know that AP is equal to 2. So what this shows us is that n times, or wait, p times AP minus 2 over p minus 1 is equal to AP minus 1. With some relatively quick expansion out, this shows us that as long as AP minus 1 is greater than 2, then AP is going to be smaller than AP minus 1. Thankfully, there's an easy proof for the fact that this sequence eventually gets larger than 2. And that's just considering the first, I don't know, let's say four examples, and the sort of worst case possible. In the worst case possible, we have the first 4 terms, that is. In the worst case possible, we have 1 plus n minus 1 over 2 over n plus n minus 2 over 3 over n plus n minus 3 over 4 over n. And we can remove the floors because in this case this is divisible by 2, this is divisible by 3, this is divisible by 4. Because if they weren't divisible by those values, then n would either have to be, or n minus 1 would have to be, or n minus 2 could be. In either case, the value overall would be higher than this sort of worst case interpretation. Now, quickly doing this, we realize that this overall actually comes to 25n minus 46 over 24n. Which, of course, can simplify to, this is 1 plus. This is the same as 2 plus n minus 46 over 24n. So as long as n is greater than 46, then it absolutely has to be greater than 2. In reality, it becomes greater than 2 much faster than before n equals 46. But in this case, this is all we need, as take p as a prime greater than 46, and we have done the second part of the question. Now almost back to the first part. We have to prove that an plus 1 is greater than an for infinitely many n. In my mind, the easiest way to do this part, and the first way I approached it, was to take sort of incredibly large, or now that we've investigated a bit, it seems like this function, this sequence, does overall increase by quite a bit. So take really large gaps, and then there has to be somewhere in between where it increases. Because if you imagine, if you have something, if we look at sort of n here and n here, if we know there is 1 point here, and we know there's 1 point here, somewhere in this gap, there has to be an increase. Otherwise, it just won't work. So, what I used for this were powers of 2 with 2 to the n, or let's use a different variable, 2 to the m and 2 to the 2m. First of all, we have to investigate how these actually work when we put them into the function. When we take, n equals 2 to the m. So what this will do is we have a 1 over 2 to the m here, 2 to the m plus 2 to the m minus 1 plus 2 to the m minus 2, this would be for 3, and 2 to the m minus 2 again. And as it turns out, since this is 3 and then 4, there will then be 4 but for the next power of 2. So we can write this as 4 times 2 to the m minus 3. And then there will be 8 for the next one. This is assuming m is large. All the way until we have 2 to the m minus 1 times 2 to the m minus m. This would be all the ones at the end. This is obvious because when you get under 2 to the m minus 1, there are 2 to the m minus 1 things still remaining, and all of those will have a floor of 1, as they're less than 1. No, sorry. They will all have yeah, they will all have a floor of 1 because they are all greater than 1 but less than 2. So, now what does this actually total to? So we have 1 in front, then we have a half plus another half plus another half. We actually have as many halves as it takes us to get to the m minus 1. In other words, we can also write this as the difference between m minus 1 and m minus m, which is the difference between minus 1 and minus m, which is m minus 1 halves. And it should be fairly obvious, if we replace m with 2m here, this will grow. And so, therefore, we have completed the first part of the question, because, as explained earlier, between 2 to the m and 2 to the 2m, the value of the sequence will increase, and so somewhere in between, let me write this out more formally. As long as this obviously only works when we take a sufficiently large value of m, at least to get the 4s and 8s and other parts. What this means is somewhere between this, I'm going to write this as 2 to the m plus I has to be less than 2 to the m plus I plus 1. So therefore we have done the second part of the question, we've done the first part of the question and the second part, although in reverse order.